Okay, so our first speaker is Talia Moore. Talia is an assistant professor of robotics and mechanical engineering at the University of Michigan. She is doing research on biomechanics, evolution, and ecology of animals, and also to create bio-inspired robotic systems. And today she's going to share with us some of her most recent research. Talia, stage is yours. We are very looking forward to your talk.
Thanks so much, Majid, and thanks, Steve, both of you for inviting me to this workshop. I'm not talking about humanoid locomotion today, but I will be talking about agile bipedal locomotion. So let's get started. I want to talk to you about gait transitions. And so gait transitions are quite common in the everyday lives of legged animals. So please watch this dog in brown here as it plays and goes from kind of a trot to a bound. And this is totally effortless and a part of play and agility in so many animals. And it's something that we see across so many legged animals. What about in robots? So smooth gait transitions are pretty difficult to achieve in legged robots. Sungbae Kim's group has achieved this in their cheetah robot, but most robots, even Spot from Boston Dynamics, either require a large input of energy to transition between gaits or to stop entirely before starting a new gait. So you notice how they show you the gaits one by one, because they actually have to stop entirely before transitioning to a new gait. So how do we make robot gait transitions more like animal gait transitions? Well, first, we have to understand how and why animals use their gaits. So most animals with multiple gaits are cursorial, meaning that they are specialized to travel long distances by minimizing the cost of locomotion. So different footfall patterns minimize the cost of locomotion at different speeds. And I want to get rid of this, but whatever. So they transition between gaits as they increase their speed. So what you see here is a study done by Hoyt and Taylor in 1981, where you have the running speed of different horses and then the oxygen consumed by those horses on the y-axis. And the different gaits are represented by these diagrams here. And what you see is that they select different gaits in different speed ranges, and those coincide with minima of the cost of locomotion, that oxygen consumption. So for cursorial animals, we can assume that they move in dynamically similar ways. So we can actually use the same dynamic model to describe their motion, and we can use similar methods, similar experimental methods to study them. But how does this energy consumption decrease? Why does that even happen? This is because there are elastic elements, the tendons, that are passively recycling energy during running. It acts as a spring and stores and returns energy with each step, which is what you'll see in this video here. So the tendon is acting as a spring, it's storing and returning that energy. And this is really important for cursorial animals, including humans. The way that we model this kind of energy storage and return is using a spring-loaded inverted pendulum model, which many of you are probably very familiar with. And this model is used to describe the motion of different animals, but it's also been used to help inspire the design of different robots. So these bio-inspired robots like Uniru from 1993 in Mark Raybert's lab, all the way until now, which is Cassie, the agility robotics robot that was based on a cassowary. And this is these are exemplars of this trend towards designing large robots with low cost of transport. So here we have log body mass on the x-axis, and then we have the cost of transport on the y-axis, which is basically how much energy it takes to move a kilogram of your mass for 1 meter or 1 kilometer. And what you see here is there's kind of this diagonal trend towards the lower right corner, right? So small animals tend to have a higher cost of transport, and then larger animals tend to have a lower cost of transport. So they're more economical in their locomotion. We also have things like ice skaters, airplanes, and cars and motorcycles here in this range because they're very efficient because a lot of them have wheels. And so this plot has been taken by a lot of the robotics community as almost being kind of a cost function. This concept of lower equals better in terms of cost of transport. And so some of the early robots have been Big Dog and Asimo that had maybe a higher cost of transport than you would expect for their size if they were an animal. And we're moving more towards robots that have a lower cost of transport than you would expect for their size. But what does this mean for Gaits, and what does this mean for agility? Well, because these are, we're assuming that these are all based on cursorial locomotion and it's all dynamically similar, we can make some assumptions about dynamically similar motion. So dynamic similarity means that if two pendula have lengths and times in constant proportions, then so are the velocities, accelerations, and forces. And so from this, we can derive the Froude number, which is the ratio of the inertial to gravitational force. So that Froude number you can also write as velocity squared divided by gravity times the leg length. If we assume dynamic similarity and this shared goal of minimizing the energetic cost of locomotion, then the speed of gait transitions can be reliably predicted for any animal or robot. So if you're quadrupedal, then you're going to have a walk to trot transition at around Froude number of 0.5, which you see here, and then a trot to gallop at around 2.5. If you're bipedal, then you're probably going to switch from walking to running at about Froude number of 1. And if we take this Froude number approach and we re-examine our robots, these robots are mostly actually attempting gaits outside of their Froude-predicted speeds. So this jog in the spot robot, it looks kind of like it's stepping on hot coals, and that may be because it's attempting this at a really, really low speed when you would usually see trots at a much higher speed for this leg length. So what else have we learned about these robots now that we've been kind of designing them and running them around in the world? The other thing that we found is that robots designed after cursorial animals are not actually very maneuverable. So if you take a look at the Big Dog from Boston Dynamics, Rex moving on granular media, and Cassie from Agility Robots that is stepping on a crack in the concrete and then falls over, these robots are not very maneuverable. And why is that? Well, it turns out that cursorial animals are not always very maneuverable either. This kangaroo, which is a cursorial animal, is not very good at getting out of the way when it's in danger. So it turns out that biologists have known for a long time that there is this fundamental trade-off between energy savings and maneuverability. And the exemplars of this trade-off are the kangaroo, which is very cursorial. It has incredible tendon energy storage. It's like the world champion of tendon energy storage, and therefore it can have very low muscle contribution. Its locomotion is very economical, but it's also very predictable. On the other end of the spectrum, we have ricochettal animals, so non-cursorial locomotion. We have ricochettal animals like this Jerboa, which have high muscle contribution and low tendon energy storage, and their locomotion is very costly and maneuverable. So this Jerboa, it has this high cost of transport. So it's actually, I made the calculations, it's off the chart here in terms of the cost of transport. It's incredibly high, and it's got a very low body size. What does this mean for its maneuverability? We'll take a look at this video that I recorded of us trying to catch a Jerboa in Western China. It's really, really difficult. This is actually the cropped last half of the video of us trying to catch this Jerboa. The other thing that's really cool about Jerboas as opposed to other bipedal rodents is that Jerboas have multiple gaits. So Happold in 1967 defined these gaits by speed. So he said that there was slow jumping or pottering, there was a medium speed gait and a fast speed gait. But since Hildebrand's work in kind of the 80s, gaits have been generally characterized by footfall pattern. And so I redefined Jerboa gaits by footfall pattern in an earlier paper of mine. I identified hopping, which is simultaneous footfalls with only one aerial phase. That's in 10% of the trials. And then skipping, which again only has one aerial phase, but it's a slightly staggered hop with no aerial phase in between. And then we've got running, which is just like our running. So it's got an aerial phase in between each step, and the legs are exactly opposite from each other. Now, there were some other trials where it was really difficult to determine the gait, so I just kind of reported them as unclear in the paper. But so I've got these three very clear gaits. And what I found by recording these data is that if we take a look at the Froude predictions, they're totally off. Froude numbers can't really be used to predict which gait a Jerboa is going to be using at a particular speed, and that's mostly because they're using the skip across their entire speed range. Instead, what I found is that the acceleration, not the speed, is a better predictor of gait use. And this means that the gaits are probably very dynamically distinct. The other thing that I found is that the Jerboas are frequently transitioning between these bipedal gaits at a broad range of speeds. So 42% of all the trials involved some sort of gait transition where they were going from one to another. And I thought that was really interesting because frequent transitions between dynamically distinct gaits enhances maneuverability. But that also made me wonder, how is it possible that these gait transitions are possible at arbitrary speeds? And maybe this is the key to some kind of agility. If we can find out how that works, then maybe we can find out how to become more agile. So if we take a look at this plot again, maybe it's not just this 2D plot of body mass and cost of transport, maybe it's a 3D plot where we've got maneuverability kind of coming out of the screen at you, and the Jerboas happen to be really high in cost of transport, but also really, really high in maneuverability. And maybe if we figure this out, we can start to use maneuverability as a cost function as we're designing new robots. But first, we need to model it to see how it works. So with my collaborators, Jiayu Ding and Zhenyu Gan, we built a modified slip model. And the key to this modified slip model is this torsional spring that controls passive leg motion. So the leg in swing, that motion is controlled by this torsional spring. So this is the full model with all of its parameters, but I want you to know that later throughout the talk, I'm going to be using this more simplified icon to describe the parameters of the model. The most important characteristics here are omega is the torsional spring stiffness, which you see here, and then phi, which is the anchor angle of the torsional spring. So this is the anchor of that torsional spring, and the angle of that with respect to the center line is what we're going to be calling the neutral leg swing angle. And that's really important, as you'll see in a minute. So to find the appropriate parameters for this model, we went back to the Jerboa locomotion and we used optimization to find the parameters that generate dynamics and kinematics that match empirical data. And so we found that the motion in the Y and the X axis matched pretty well the real Jerboa, which you can see with the dashed line. The model is in the solid line. And then we also found that we were able to match the neutral leg swing angle of the left and right legs as well. So then once we had the parameters for the model, we searched for gaits using a boundary value approach. We found 5, not 3, 5 formally described gaits. So the first one is walking, which is just like you and me walking. It's totally normal, so we didn't make an icon about it. But then we've got hopping, which I've described to you before, and here's the model hopping alongside the Jerboa with the gait diagram in the corner here, right here. And then we've got skipping, which I described to you before. So again, we've got touchdown, touchdown, and then lift off, lift off. So there's a small double support phase and two small single support phases, but only one aerial phase. And then we found this new thing that is a description of something I found earlier in the Gait and didn't really know how to describe, which we're calling an asymmetrical run. And then we've got the run, where we've got two aerial phases and they're equal in size, and each leg has its own single support phase. So let's dive more deeply into the asymmetrical run. This is the model performing an asymmetrical run, and you can see the gait diagram here. There's a small aerial phase in between the left and the right feet. So as it goes, oh, let me move that, get it to work. I'm going to do this again. Okay, so as it goes, you see that there's an aerial phase between both of the footfalls, but it's much smaller than the aerial phase between the other two footfalls. And so we've got two aerial phases that are unequal. Does the animal do this? Yes, the animal does this as well. Here's two aerial phases that are totally different sizes. And so this actually helped me to solve some mysteries from my previous data and helped me sort out what those kind of questionable trials were from the Jerboa data. So once we had this model, we created what we're calling the gait structure. And so this is kind of a three-dimensional plot with these different parameters. And each dot on the continuous colored lines here represents a unique set of parameters at which a periodic gait is feasible. So we start with one set of parameters, like say we start right here, and then we perform a numerical search using a continuation approach, testing the neighbor parameter values for viability. And so we're basically just tracing along here as we go and finding all of the viable gaits. So I'm also showing you a 2D projection of this three-dimensional plot to show you that there are two distinct continua here. So there's a continuum for the symmetrical gaits, which are walking and running, which you see here. And then there's a totally distinct continuum for the asymmetrical gaits, including hopping, skipping, and asymmetrical running. So sometimes there are multiple neighbors that work, or the neighbors have different gait solutions. And these are called bifurcations or gait transitions, which are represented by the black shapes. You can see the circles, the triangles, and the diamonds here. At this baseline, where the neutral leg swing angle is 0, transitions can only occur within each continuum. So you can only get from asymmetrical gaits to asymmetrical gaits, or walking or symmetrical to symmetrical. You can't really go between the two. But we know that Jerboas go between the two all the time, and we don't really see these gait transitions just at these rigid moments in speed, right? We don't really see them just at these single speeds. We see them across the entire speed range. And so we're trying to find out what are the mechanisms that we can find to diversify these gait transitions. And we found two. First, let's talk about coupled changes in neutral leg swing angle. So coupled changes in neutral leg swing angle give you, in this gait diagram, both the left and the right leg, their anchor has moved from the baseline. Now I'm showing the baseline gait structure here in faded colors and the new neutral leg swing angle gait structure in the bolder colors. The structure is overall the same, but has just shifted in space a little bit. So now let's examine just the transitions from skipping to asymmetrical running. Each color here, each kind of fade of that blue here represents a different neutral leg swing angle. So not just plus 0.4 radians like you see on the left side here, but it sweeps through multiple different coupled changes in neutral leg swing angle. What we see is that the same number of transitions exist, but the speed changes very slightly, especially for the lower speed transition. So we still get the same number of transitions, they just kind of move in space, move in speed. So these coupled changes in neutral leg swing angle shift the speeds of existing gait transitions. And that means that there are no new transitions and there are no transitions between the continua. Next, let's talk about the decoupled changes in neutral leg swing angle. So here I'm showing you how in this gait diagram, the left and the right side have switched. Their anchors have decoupled and they've got these different neutral leg swing angles. Again, the baseline is faded here and the new neutral leg swing angle values are in bold. So see how the shape of the structure changes so much, even with these small changes in neutral leg swing angle. This is the left leg with 0.06 radians, and then here it is with the left leg at 0.03 radians. And even with these small changes in neutral leg swing angle, we've got a totally different shape to that gait structure between skipping and asymmetrical running. We go from kind of a partial loop all the way to a closed oval. If we look at the transitions across many different neutral leg swing angles, we sweep across those. These transitions happen across the entire speed range. This also introduces new transitions between the symmetrical and asymmetrical continua. So these asymmetrical gaits span everything between baseline running here, all the way to hopping here, which is an asymmetrical gait, right? And so running is in yellow here and hopping is in red. And that's going to be this transition between the symmetrical and the asymmetrical. They're totally overlapping and spanning that entire gap. So with decoupled changes in neutral leg swing angle, we're creating new gait transitions. And this allows us to transition at a broader range of speeds and between continua, which we couldn't do before with the coupled changes. Now, we compared our model transitions to the empirical data, and here's kind of a gait diagram from a diagram of the gait transitions from my previous work when I only knew about 3 of the gaits. And what I found is that most transitions involve skipping and asymmetrical running, which is the same between the model and the empirical data. Most transitions use the uncoupled neutral leg swing angle mechanism, which is exactly what the Jerboas use. And the transitions occur across the entire speed range. So building this model actually helps us to understand gait control a lot better. So I don't know if you know about the DMRT3 stop codon mutation. It's this gatekeeper gene that allows horses to perform this tolting locomotion. So that's a normal and that's a tolt locomotion. So I'm wondering if these decoupled neutral leg swing angle transitions are facilitated by this mutation in the stop codon that allows them to uncoordinate their legs. And this is also currently informing the design of a smooth gait transition controller for legged robots. And so what I urge you to join me in is designing energetically costly agile locomotion. So instead of being kind of in this corner here, I'm shooting for this corner over here, where we have highly maneuverable and highly costly locomotion. So thank you for watching, and thanks to my co-authors, Jiayu Ding and Zhenyu Gan, and here is a link to our paper. All right, thanks.
Great. Thank you so much, Talia. It was very interesting. So if you have any question, either you can write it in the chat or you can just raise your hand and ask it here. So Steve, if you want to ask questions if there's any question from audience, you can also ask.
Yeah. Well, while we're waiting for people to gather their thoughts, I have a quick question. I imagine that in addition to the kind of the trade-off between efficiency and maneuverability, you probably have a similar relationship between the other axis, right? Like the total mass of the system, of the animal or the robot, and maneuverability. Is there anything that you can comment on or suggest if we have a robot in the 20 to 50 kilo range? It's very self-interest.
Yeah, I agree. Yeah, that's a really good point. I think that having a large mass is going to limit your agility greatly because you're always going to have to redirect that mass as part of the definition of agility. But I think that if you have these different gaits and you have a way to transition between those gaits really easily and yeah, I think that that still can help you to have slightly more agile locomotion. Like if you take a look at the Boston Dynamics Atlas robot that's doing all these like parkour in their videos, they are changing kind of between gaits a little bit and programming those in. But I think that this strategy may be viable at many different body sizes. It'd be something fun to explore.
Okay, Joao, do you want to unmute yourself and ask a question?
Yeah, I have a question. So great talk, Talia. It's always awesome to see biomechanics talks among roboticists. I always enjoy those. One question that I have is regarding the, this is sort of energetic talk has been something that is kind of, in my point of view, like old news for robotics. Now people try to do other things. And I think a lot of the reason because, motors like to operate at a drastically different regime than muscles, right? So muscles don't want to, robots want to move much faster, lower torque, which would probably bias them to different gaits, right? I remember some work with the cheetah showed that, trotting, galloping, etc., was kind of like the same energetic cross across the board. So there was no actual advantage of doing any of those. So in your point of view, how do you think we should think about these cost of transport and things of that sort when, the actuator is fundamentally different and, how does that work from your point of view?
Yeah, this is a fascinating question. And maybe this is something I'll bring back as a discussion for my lab group, actually. This is great. So yeah, I think that a lot of this can help us even in the design and selection of our actuators as well. So if we want a lot of elastic energy storage, then maybe we're using series elastic actuators. If we want something that is going to have like a really high frequency and maybe not a ton of torque, then maybe we look for something like electrostatic, like an electroactive polymer or something like that. And so I think that what we can do is start to look at a lot of different non-traditional actuators and not just these motors like direct drive or quasi direct drive actuators that you would get on a traditional electric robot, and start looking at kind of this wide array of actuators that are being developed right now across universities, and start to think about how they can be leveraged to make these unusual forms of locomotion. Okay, so online, Varun is asking what factors determine which gait Jerboas select in the wild and which do they use most frequently? So this is something that I am still actively trying to understand. I think based on what I've seen in the lab, I think that they use the skipping gait most frequently. And a lot of this is just like hunches right now that I'm trying to investigate more rigorously in the lab. But the skipping gait I think of as sort of their most maneuverable gait, and one in which they can transition to whatever else they need to do. So they can switch from left to right leading as well, from step to step. The other thing is that the hopping gait, like the symmetrical hopping gait, they tend to use that for high and low acceleration. So if they're starting from nothing and they really have to just like book it right away, or if they really have to decelerate before hitting something, they use that hopping gait. And then the running gait, I think that they use when they're kind of maintaining both direction and speed and not really doing anything too strenuous. But all of this is really just kind of conjecture at this point. And this is something that I'm actively trying to figure out, especially in the wild. Great question.
Okay, great. Thank you, Talia. So is there any question, Steve, from audience, or we can wrap it up here?
No, I have a very quick question before we switch to the next speaker, if I may. Just anecdotally, have you noticed if they prefer different gaits at like a different set of gaits throughout different stages of their development, as when they're juvenile to when they get older?
Yeah, so there's actually a great paper by David Eilem about this called the developmental order of Jerboa gaits, like creeping, pivoting, and something like that. And so when the Jerboas are little babies, their feet are the same size with respect to their body as mice would be. Like they're kind of the same shape as mice. But then after they're born, their feet just start growing at huge rates. And this doesn't happen in the womb. This happens post-birth. And so as their feet are growing, they're kind of turning into these giant skis under their body. They're trying to figure out how to move around on this. So first they're kind of like moving back and forth, kind of like squishing around like a slug. And then they start to get their legs under them and they go quadrupedal and even maybe pentapedal because their foot or their tail sort of acts as a pseudo foot. And then they start to like come up a little bit more. So there's like a whole paper on how the gait selection changes as they grow up and as their body like shape changes. And it's wonderful. It's got beautiful figures. I highly recommend it.
That's super cool. Thanks.
Okay, great. Thank you very much.